Next topic is linear combination, shortly denoted by L dot C dot. Let V be a vector space and U bar, V1, V2, Vn bar belongs to V. That is the vectors of vector space V, elements of V. Then if U bar expressed in the form K1 V1 bar plus K2 V2 bar plus dash 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 Kn Vn bar, right here Kn Vn bar. What are K1, K1, K2, Kn, where K1, K2, Kn are scalars, that is the real numbers. Then we say that U bar is a linear combination of V1, V2, Vn. That is, if one of them, this U bar, express the sum of these type vector K1, V1 plus K2, V2 plus dash 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 Kn, Vn. What are K1, K2, Kn are scalars. Then we say that U bar is a linear combination of V1, V2, Vn. And if U bar not expressed in this form for any K1, K2, Kn, then we say that U bar is not linear combination of these n vectors. Okay. So the two type questions show that this 1, 2, 3, that is suppose U bar as a linear combination of 1, 1, 1, 1, 0, 1, 0 and 0, 0 minus 1. And the second one is again 1, 2, 3 is not linear combination of these three vectors. So two type problems. So when we denote this 1, 2, 3 as U bar, this 1, 1, 1 as V1 bar, V2 bar and V3 bar. And now we have to express this U bar as a linear combination of V1, V2, Vn. That is, we have to find the K1, K2, Kn scalar such that U bar is equal to K1, V1 plus K2, V2 plus K3, V3. These K1, K2, K3, these scalars exist. Then we say that U bar is a linear combination of V1, V2, V3. So this is U bar expressed as a linear combination of V1, V2, V3. So if this K1, K2, K3 does not exist, then we say that U bar is not linear combination of V1, V2, V3. That is, for any values of K1, K2, K3, this U bar is not expressed in this form. Then we say that it is not a linear combination. It is in the second problem. So in the first problem, so the answer of both problems are same. But in the second problem, we does not have the values of K1, K2, K3. And in this problem, number one, we have the values of K1, K2, K3. Some real numbers for K1, K2, K3, values of K1, K2, K3. So let K1, K2, K3 be scalars such that U bar is equal to K1, V1 plus K2, V2 plus K3, V3. Okay. Then we have to find the values. We have to solve this equation and we have to find the values of K1, K2, K3. So this is called linear combination. So one vector is a linear combination of 3 vectors, 2 vectors, 4 vectors, or 5 vectors, n vectors. Okay, or one vector is not linear combination of 3 vector, 2 vector. Okay, so U bar as you let K1, K2, K3 be scalar, say that U bar is equal to K1, V1 plus K2, V2 plus K3, V3. Now we have to find the values of K1, K2, K3 by solving this equation. So write U bar as 1, 2, 3, V1 bar as 1, 1, 1, V2 bar 0, 1, 1, and V3 bar 0, 1, 1, 1 minus 1. And then apply the definition of scalar multiplication in R3. Usual scalar multiplication, that is multiply by K1, multiply by K2, multiply by K3. We have these 3 vectors. And then add these 3 vectors as the usual addition in R3. Or these are 1, 1, 3, 1, 2, 3, 1, 1, 1. All these are the vectors of R3. These are the vectors of R3. So now apply the R3 is the vector space under usual addition and usual scalar multiplication. Now use the usual addition, definition of usual addition. So K1 plus 0 is K1. Then K1 plus K2 plus K3 as the second element. And then K1 plus K2 minus K3 as the Z coordinate. And then compare the LHS and RHS. We have K1 is equal to 1. K1 plus K2 plus K3 is equal to 2, and K1 plus K2 minus K3 is equal to 3. Now we have to find the values of K1, K2, K3 after solving this system. And we know that this system is solved by using the 2 methods in the first chapter, Gauss elimination method and Gauss-Jordan elimination method. Now here we apply the Gauss elimination method. And we know that the system is either consistent or system is inconsistent. That depend on the rank of A and rank of AB. So what is AB? augmented matrix. We write the augmented matrix. So already we have seen the systems in the first chapter. That is either the systems are consistent or the systems are inconsistent. And this is non-homogeneous system. It may be inconsistent. So if the system is inconsistent, means K1, K2, K3 does not exist, and in that case we say this vector is not, U bar is not linear combination of V1, V2, V3. But if the system is consistent, means we have the solution of the system, means we have at the values of K1, K2, K3 either unique or infinitely many. And if the system is consistent, then we say that U bar is a linear combination of V1, V2, V3. So what is the cases for this system? Either the system is consistent or inconsistent. These are the two cases. And if the system is consistent, then system has unique solution or infinitely many solutions. So if the system is consistent, either has infinitely many solution or unique solution, in both cases we say U bar is a linear combination of V1, V2, V3. But if the system is inconsistent, if the system has no solution, that is K1, K2, K3 does not exist, which satisfies all these three equations simultaneously, means U bar is not linear combination of V1, V2, V3. This happens in the second problem. This is not happens in the first problem. So this system, we have to solve this system by using Gauss elimination method. So form the augmented matrix as a coefficient of K1, K2, K3, and then constant coefficient is equal to, then K1, K2, K3, 1, 1, 1, and the constant coefficient is equal to 2, then 1, 1, minus 1, and 3. So this is the augmented matrix. The combination, this matrix first three columns form the matrix A, and this is the matrix B, matrix of constant, and this combination of A and B, A matrix and B matrix, is the augmented matrix AB. Combination of A matrix, coefficient matrix, and matrix of constant. And then we have to reduce this matrix to echelon form. So first here it is 1. So reduce this one and this one to 0. So R2 minus R1 and R3 minus R1. So first row as it is, the second row change is this, the third row is this. Then we have to reduce this element 1 in the third row, R3, by using this 1 to 0. So R3 minus R2, we get the first row as it is, second row as it is, and the third row 1 minus 1 0, 1 minus 1 minus 1 minus 1 become minus 2, and 2 minus 1 becomes plus 1. So right here plus 1. R3 minus R2, 2 minus 1 is 1, not minus 1. Here write plus 1. It is not minus 1. It is plus 1. Okay. Then minus 1 half R3. We have to reduce this minus 2 to 1. To 1. Because we have to reduce this matrix to echelon form. So reduce this matrix, element minus 2 to 1 by using this operation minus 1 half R3. So the change in the third row. So here we have 1, right, plus 1, and here 1 by minus 1 half into 1 is minus 1 half. It is now correct, minus 1 half. 2 minus 1 is 1. So here is 1. Then after multiplying by minus 1 half, we have minus 1 half. So this is an echelon form. When we say the matrix is an echelon form, we know that if each row first non-zero element is 1. In each row, first non-zero element is what called leading one, and the leading of one of lower row is to the right of the leading one of upper row, and if there is 0 row, then it is at the bottom of the matrix. So if these three conditions are satisfied by the matrix, then matrix is called in echelon form. So this is an echelon form. So rewrite the equation like this. We have this matrix form, this equation. Now we have to write the equations from matrix. So K1 into 1 is K1 plus 0 into K2 plus 0 into K3 is equal to 1. Then 0 into K1 plus K2 plus K3 is equal to 1. And then last is K3, 0 into K1, 0 into K2, K3 is equal to minus half. And so we have the values of K2 as a substitute K2, K3 as minus half. So minus half becomes plus half. So 3 by 2. So K1 is 1, K2 is 3 by 2, and K3 is minus half. So we have the values of K1, K2, K3, and therefore 1, 2, 3 is equal to. So write the values of K1, K2, K3 at this place. So 1, 2, 3 is equal to K1 is 1 into 1 1 1 plus K2 is 3 by 2 0 1 1 1, and K3 is minus 1 half 0 1 1 1. So in order to tally the example, this is now what we have 1 2 3 expressed in the linear combination of these three vectors. So u bar is a linear combination of v1 v2 v3. So don't write these two steps. This is to tally the example. So if I have to tally this is correct, then write multiply by 1, that is apply the method of definition of scalar multiplication, multiply by 1 in bracket, multiply by 3 by 2, multiply by 1 half minus 1 half, or 1 half take here minus sign, and then their addition and subtraction is again the same element 1 2 3. So don't write these two steps. Directly after this step, what we say that u bar is a linear combination of v1 v2 v3. We have the values of k1 k2 k3, and therefore u bar is a linear combination of v1 v2 v3. If we does not have the values of k1 k2 k3, then we say the u bar is not linear combination of v1 v2 v3. So don't write these two steps. In order to tally this is correct, then we write these two steps. Then we take these two steps roughly, that is multiply by 1, multiply by 3 by 2, multiply by 1 half, and then we have the addition and subtraction is equal to again the same answer 1 2 3. So in order to check whether these k1 k2 k3 are correct, then we have to tally this, that is we have to apply the definition of scalar multiplication and addition. We have the answer same 1 2 3. So after this we have the values of k1 k2 k3, therefore u bar is a linear combination of v1 v2 v3. Now next example, we have to again verify whether this u bar as a 1 2 3 as a linear combination of these three vectors v1 v2 v3. So naming that u bar is this 1 2 3, this is v1 bar, this is v2 bar, and v3 bar. And now apply the same procedure, that is we try to express this u bar as a linear combination of v1 v2 v3. So naming u bar v1 bar v2 bar as v3 bar is this. Let k1 k2 k3 be scalar such that k1 v1 u bar is equal to k1 v1 bar plus k2 v2 bar plus k3 v3 bar, right? K1 k2 k3, here k1, here k2, and here k3 v3 bar. So let k1 k2 k3 be scalars or real numbers such that u bar is equal to k1 v1 bar plus k2 v2 bar plus k3 v3 bar, and then substitute u bar as 1 2 3, v1 bar as 2 minus 1 3, v2 bar as 4 1 2, v3 bar as 8 minus 1 8. Then apply the definition of scalar multiplication. Multiply by k1 to this vector 2 minus 1 3, we have 2k1 minus k1 3k1 plus multiply by k2, so 4k2 k2 2k2, and multiply by k3, we have 8k3 minus k3 plus not plus comma 8k3, and adding these three elements by using definition of addition in R3, that is the usual addition of corresponding components. So 2k1 plus 4k2 plus 8k3 as the first element, comma, right in round bracket, comma, minus k1 plus k2 minus k3 as the second component, comma, 3k1 plus 2k2 plus 8k3 as the third z component. And then compare the LHS and RHS. What do we have? Therefore, we have 2k1 plus 4k2 plus 8k3 is equal to 1. Then minus k1 plus k2 minus k3 is equal to 2. And 3k1 plus 2k2 plus 8k3 is equal to 3. So we have to solve these three equations, that is this system, and we have to find the values of k1, k2, k3. So form the augmented matrix. So what is the augmented matrix? 2 4 8 1, then minus 1 1 minus 1 2, and then 3 2 8 and 3. So this is the combination of, this is the matrix A, and this matrix is, this is the matrix B, and the combination of A and B is the augmented matrix AB. And now we have to reduce this matrix to echelon form. So 1/2 R2 R1 as the application, or interchange the first and second row and multiply the now first row by minus 1. So this is the another way to obtain here 1. So in order to avoid the fractional, like the 1/2, we have to interchange these first two rows, first row and second row, and then multiply the first row by -1, we have 1. Or we, in another way, 1/2 R1 multiply by first row by 1/2. So we have 1, 2, 4, 1/2. And the second row as it is, third row as it is. Then we have to reduce this -1 and 3 to 0. So the operation are by using 1. So the operation is R2 plus R1, and then R3 minus 3 R2, minus 3 R2, not plus 3 R2, minus 3 R2. Okay, R3 minus 3 R1, minus 3 R1, not R2. R3 minus 3 R1. And then we have, so use that operations sequentially. So we have this matrix. Then we have to reduce this 3 to 1. So 1 by 3 R3, R2 as this. To avoid this fractional numbers, use the another operations. But if we have, this is the echelon form. So use the method, and then we have the echelon form. This is the echelon form. This is the echelon form. So what is the method to reduce this matrix to echelon form? Reduce this element to 1, then obtain the 0 below that too. Then reduce this element to 1, then obtain 0 below that, and then reduce this element to 1. If the element, this element is suppose 0, after these 3 are 0, then reduce this element to 1. So like this. Here we have 3, and then we have to, after this step, we have to reduce this element to 1. Okay, 1, then below 0, 1, then below 0, and then 1, but it is 0, and so 0 element, if we multiply any number to 0, it is not equal to 1. So we have to reduce the next element to 1. So reduce this element to 1. So 1 by 3 R3. So we have 1, and this is an echelon form. So this echelon form is not unique. This depends on your calculation. So someone have the another echelon form, but the answer of the problem, that is the values of K1, K2, K3 are fixed. For example, in this example, this is an echelon form. This echelon form is depend on your calculation. This is not unique. This echelon form of the matrix is not unique. It is depend on your calculation. That is the answer of this echelon form may be vary from the students to students. Okay, so it's depend on your calculation, but these values of K1, K2, K3 are unique. We have the value of K1 as 1, K2 as 3 by 2, and K3 as -1/2. So these values are same of all of you, but the echelon form may be have different form. Okay, different answer or this echelon form. So but the answer of K1, K2, K3 are same, are unique. Okay, so therefore in case of the infinitely many solutions, the values of K1, K2, K3 looks differently. Their forms are different, but the answers are same. So this is an echelon form. Someone have the different echelon form. It's depend on the calculation. But after rewriting the equation, what we have, K1 plus 2 K2 plus 4 K3 is equal to 1/2, and then K2 plus K3 is equal to 6 by 5, and lastly we have 0 into K1 is 0, plus 0 into K2 is 0, plus 0 into K3 is 0. So 0 plus 0 plus 0 is 0 is equal to 1, and which is absurd, which is wrong, which is impossible. 0 is equal to 1, and therefore the given system is inconsistent. Why the system is inconsistent? We have this type of 0 is equal to 1. So this is the one answer format of one answer. Or we have learned in the first chapter that what is the rank of this matrix A. So this is the echelon form of the matrix A. These first three rows, these first three columns, this is an echelon form of the matrix A. And how many rows, non-zero rows in this matrix are 2, and therefore rank of A is 2. And this whole is the echelon form of the matrix AB. And what are the number of rows in the matrix AB? So there are 3 rows. There are 3 rows in this matrix, non-zero rows. So this row is non-zero, this row is non-zero, this row is non-zero. So total this matrix is the echelon form of the matrix AB. And so from this, what is the rank of AB is 3, because what is the rank of the matrix? Rank of the matrix is equal to the number of non-zero rows in its echelon form. So this is the echelon form of the matrix AB. And so rank of AB is 3. And this after cancelling this last column, the remaining matrix is the echelon form of the matrix A. And so this is the this is the non-zero row, this is non-zero row, and this is the zero row. So in the echelon form of the matrix A, there are two non-zero rows, and therefore rank of A is 2, rank of AB is 3, and rank of AB is not equal to rank of A, and therefore the given system is inconsistent. So write either this type answer, that 0 is equal to 1 is impossible, absurd, and therefore the system is inconsistent, or write that rank of A is 2, rank of AB is 3, and therefore rank of A is not equal to rank of AB, and therefore the given system is inconsistent. Means what? K1, K2, K3 does not exist. This means what? We this K1, K2, K3 does not exist. That satisfies this equation U bar as K1 V1 plus K2 V2 plus K3 V3. Such a K1, K2, K3 does not exist, which satisfies this equation. And therefore we say that U bar is not linear combination of V1, V2, V3. So these two examples shows the whole idea about the linear combination. So when we say one vector is linear combination of the remaining three vector or two vector or four vector, if the values of K1, K2, K3 exist, either unique or infinitely many. But if the system is inconsistent, means if we does not have the values of K1, K2, K3, and then in that case we say the vector is not linear combination of the remaining 3 or remaining 4 or remaining 2. So in the second example, the method to solve the example of the type linear combination and not linear combination, both the examples are, the method to solve both the examples are same, but only the last two sentences are different. That the system in the previous problem, the system is consistent. If you observe the previous problem, then what we have? What is the rank of A? Rank of A is 3, and rank of AB is also 3. If you observe this echelon form of the previous example. So these first three columns are the echelon form of the matrix A. So this is non-zero row, this is non-zero row, and the 0, 0, 1 is also non-zero row. So echelon form of the matrix A contains three non-zero row, and therefore rank of A is 3. And the whole, if you consider this whole matrix, this is an echelon form of the matrix AB, and it contains again three non-zero rows, and so rank of AB is also 3. So in this case, the system is consistent. The system is consistent. That is, we have at least one value of K1, K2, K3, and therefore the we say the vector is a linear combination of the remaining vectors. And if the system is inconsistent, when the system is inconsistent, we have like this statement: 0 is equal to 1, or we have that the rank of A is not equal to rank of AB, then the system is inconsistent. And if the system is inconsistent, then system has no solution, means U bar is not linear combination of V1, V2, V3. So it's depend on this system. So this is the non-homogeneous system, because all these K1, 2, 3 are not equal to 0. If these values of in the place of 1, 2, 3 all are 0, then it is a homogeneous system, and homogeneous system is always consistent. But a non-homogeneous system, non-homogeneous, this is also non-homogeneous system, is equal to 1, is equal to 2, is equal to 3. If all these are equal to 0 at the place of 1, 2, 3 all are 0 numbers, then it is a homogeneous system, and the homogeneous system is always consistent. But this is non-homogeneous system, so it may be consistent or not consistent. So if the system is consistent, then we say the vector is a linear combination of the remaining vectors. So this is not linear combination, and therefore U bar is not linear combination of V1, V2, V3. So these are the two problems on the linear combination. So in R3 we can also solve these types of examples for R4, for R2, for R1, and here one vector is linear combination of the three vectors, or we can solve problems of the type one vector is linear combination of two vectors or three vectors or four vectors. So we will see the remaining problems of linear combination in the next lecture.